The next layer that we had shown in the diagram is F1 layer. It is about 180 kilometer of height and has an approximate thickness of 20 kilometers. So 180 kilometer from Earth's surface, we have a layer called F1 with the approximate thickness of 20 kilometer. It combines with F2 layer at night. Most of the HF waves are passed through it to the F2 layer. The layer provides more absorption for the high frequency waves. And the last layer that we had was F2 layer, which is most important reflecting layer for high frequency radio signals that incident on it. Its height ranges from 250 to 400 kilometer from Earth's surface, and it has approximate thickness of about 200 kilometers. It's very thick compared to the other layers in terms of the size of the thickness. The height and ionization density of this layer vary to a great extent, and due to the high ionization density, the F layer remains present even during the night times. So during the night times, the only layer that we get is the F layer, because F1 and F2 combine with each other. If present, we will have sporadic E layer also, but D and E layers will vanish during night time. If we look at this figure, it gives us some very important information of how various layers will exist throughout the 24 hours of a day. If we start from midnight, for the first 6 hours, which will have the night time 12 a.m. to 6 a.m., you can see there is no E and D layers existing. It's only F layer, which is also F1 and F2 combined together. When we talk about daytime, starting from 6 a.m. up to 6 p.m., so that's 12 hours of day from morning to evening, you can see E and D layers will be present. The very first layer will be D layer, then E layer. Then we have F layer splitting into F1 and F2. F1 will lie first, and then above F1 we will have layer F2. And you can see on F2 at very higher height in some different period of years. So when we locate F2 layer in the month of December, it is at much lower height, but when we locate F2 layer in the month of June, it is at much higher height. And that's the reason the height from Earth's surface of F2 is not fixed. It will vary, as we had seen the previous slide. It will vary from 250 to 400 kilometer, whereas all the other layers are at constant height irrespective of the time of the year that we have considered. But again, you can see after 6 p.m. when the night time starts, D and E, that means after the sun has set, D and E layers will vanish again, and F1 and F2 layers will recombine into one layer, which is F. So there is one very famous question that is asked, which says, why do we get better reception at night? That is because at night the F1 and F2 layers combine to form one layer, and the lower two layers D and E disappear. As the lower layers are absent, the absorption of the signal does not take place, which was taking place during the daytime. Even in the presence of D and E layer, the reflection mostly will take place through sporadic E layer, or let's say F layer, and hence when the signal passes through D and E layer without getting reflected back to the Earth, it will simply undergo the attenuation. Now this attenuation is avoided during night time. So this improves the strength of the reflected signal because it has not penetrated through D and E layers, so no loss of energy taking place there, and hence the quality of reception will improve at night. One more question that we must answer: how does the reflection take place? So one thing must be clearly understood, that actually the reflection of the signal does not take place. What happens is the refraction of the signal from the ionospheric layers, because some part of the signal will always cross the layers and will reflect into the space. The remaining part will come back to the Earth. The incident signal, that means signal transmitted towards the ionosphere, approaches the ionosphere where the ionization density increases. The increase in the ionization density will reduce the refractive index of the layer progressively. Due to this, the incident wave is bent further and further away from the normal. Due to this mechanism, the incident wave is reflected back to the earth. The angle of incidence and the angle of reflection are always equal. So that's all about skywave propagation, which is used for the frequencies in the range from 3 megahertz to 30 megahertz, and has some important applications like shortwave band in radio broadcasting.